So our next notion, and we're talking about limits, is how to translate these words into something more mathematical. Now let's plow this ground one more time. This is what we want to have happen: a nice smooth curve with no breaks, no jumps. I change from, and instead of having individual points, maybe it's easier to see if we have a curve. So it could be when we learned to draw the basic parabola that maybe there were some gaps in the curve somehow. It turns out there aren't, but maybe there were. How do we know this never happens? What we're going to verify is this never happens. So this is a look at the stuff we want to make sure and prohibit. We want to make sure this is right out. And what we can see here is this: that there is a scale of magnification. If I choose a small enough interval around L, that if I get closer and closer and closer to A, the function values never, ever get inside this interval. The function values always stay outside the interval, both above and below. If there's a jump, if there's a gap of any kind, then this is what's happening, and this is what we want to guarantee does not occur. We want to show that this is what happens. We want to make sure that the work we do has this occurrence, not this. It turns out that many of the techniques of the calculus do not apply in this scenario, but they do here. And if this does happen, then there are some special tools you need to develop to handle that. We'll talk about some of that stuff later on too. But this is what we want to make sure is happening. That no matter what scale of magnification, I don't care how small we take this interval around L, if we get very, very close to A, that is to say, if I choose X very close to A on the X-axis, what we want to make sure happens is the function value, f of X, the function value gets very close to L on the y-axis. As X gets closer to A on the X-axis, the f of X gets closer to L on the y-axis. As you get closer and closer to A on the X-axis, we want to make sure that f of X gets closer and closer to L on the y-axis. All right? So let's translate that. No matter how, and so when I say no matter what scale, what I mean is this: the scale is determined by the size of this interval around L. This is like my target. And what we're saying is no matter how small this target gets, you can still choose X's that get inside that target. So no matter how small the interval around L, let's translate that. For any small interval around L. That makes this, when I say no matter what scale of magnification, that's very unofficial mathematically. This is a little more mathematical because we talk about an interval now. So this is translating this part to make it a little bit more official. So what happens for any small interval around L? If we get very, very close to A, what the heck does very, very close? What we say is this: as X gets closer and closer to A, as X gets closer and closer to A on the X-axis, f of X, so I've just translated if we get very close to A on the X-axis, that's this next line. What has to happen? The function value, f of X, gets closer and closer to what? What is the f of X staying close to? F of X is staying close to L. As you get close to A on the X, you stay close to L on the Y. All right? So I have translated this piece. This is a little bit more rigid. So now, let's translate this and make it a little bit more mathematical. for any small interval around L. So now, some notation. Notation. Here's A, here's L. This is the interval around L. That distance, which is the same as that distance is denoted with the lowercase Greek letter epsilon. The lowercase Greek letter epsilon. I tend to write my epsilons like this. Some people write their epsilons like this. I don't care which one you pick, but I will tend to write it that way. This is the Greek letter, lowercase Greek letter epsilon. Right? And so what we're saying is, and usually epsilon is a very, very small number. We're not interested in what happens very far away from L. We're interested in what happens when we get very close to L. So typically epsilon is a very, very small number. We want very small magnification. The smaller the better. And so when we say for any small interval, what I'm really saying is for any epsilon. One key notion, epsilon must be given. Given any epsilon to start with, no matter what scale of magnification. Given epsilon is mathematically equivalent to saying at any scale of magnification. For any epsilon. One thing that's required is it must be greater than 0. If epsilon is equal to 0, you don't have an interval. And if epsilon is negative, it doesn't really, you generate the interval, it's reversed, and we want to get rid of the negative sign. And so for our purposes, it suffices to say epsilon must be greater than 0, strictly greater than, not equal to 0. So for any epsilon greater than 0, that is the mathematical way of saying for any small interval around L. Now, what does it mean to say as x gets closer and closer to A? Closer and closer to A. What does that mean? Well, what it means is the distance. So as the distance between x and A, what happens? What do we mean to get closer and closer? What is the distance between as they get closer? If the distance between must mean distance between is getting very small. As the distance between x and A gets small, what must happen? As I choose an x with the distance between x and A very small, what has to happen up here on the function? What has to happen is the function value must be very close to L. And what do we mean by very close? It means the distance between x and A gets small. The distance between, not x and A, here x and A is happening on the x-axis. What's happening on the y-axis? This is f of x and L. The distance between f of x and L also gets small. In fact, how small does it get? F of x must be inside this interval. F of x must be inside this interval. The distance between L and f of x, that distance must be less than that distance. The distance between f of x and L must be less than the distance between L and this point. That distance, we know what that distance is. It's epsilon. The distance between f of x and L must be less than epsilon. The distance between f of x and L must be less than epsilon. It can be too low, or maybe, here's f of x. The distance between f of x and L is less than epsilon. So when we say distance between f of x and L gets small, we know how small we want it to get. We want the distance between f of x and L is less than epsilon. And now this is really starting to smell mathematical. In fact, this next piece is going to really get us to jump into the mathematics notation. For any epsilon greater than 0. That's the math way of saying I don't care what scale of magnification you have. the distance between x and a. We know how to find the distance on a number line. The distance on a number line is you subtract and take the absolute value. Subtract and take the absolute value. That's the distance between f of x and a. Or x and a. The distance between x and a is the absolute value. Now, what are we saying? Up here, now, let me just leave this for a moment. This, we're not quite finished with this because we haven't really translate gets small. But that will cause, what has to happen on the y-axis? The distance between f of x and L, we know how to write that. The distance between two values on a number line is you subtract and take absolute value. The distance, that way it doesn't matter which one's greater or less. Take the subtraction and absolute value is distance between on a number line. It doesn't matter if the number line is horizontal or vertical. You subtract and take absolute value, that's distance between. Distance between f of x and L is less than epsilon. This is about as mathematical as you can make it. So when we say this distance becomes small, what we mean is this distance is less than epsilon, where epsilon is some interval here. Well, the natural way is to translate gets small on the x-axis in a similar fashion. And so we introduce another symbol, delta. The Greek letter delta. This is lowercase delta. Capital delta looks like a triangle. Lowercase delta looks like a D that's got a little tail, a little flag going off the side. So this is capital delta, this is lowercase delta. And so delta, just like epsilon on the y-axis, here's L, that distance is epsilon, that distance is epsilon. And we say this is an epsilon interval around L. Well, similarly on the x-axis, this is A, that distance is delta, that distance is delta. And we call this a delta interval around A. And so when we say distance between x and A gets small, what we mean is the distance between x and A, absolute value of subtraction, gets small, it is smaller than delta. Typically, epsilon and delta are chosen to be very small numbers, and so saying that something is smaller than delta means it is very small. Saying something is smaller than epsilon means it is very small. This is the mathematical translation of all those symbols, and here's what all this comes together to mean. It means all these symbols over here to the left, and this is really the guts of it that you need to be concerned with. This is really the guts of it. This, if this is happening, it means, if this is happening, it means that, and not that. This is what we need to verify, to guarantee that smooth curve is happening, not a jump. This jump is a violation because for any epsilon, I'm going to show you the violation. I'm going to show you the violation. Look, do you see it? If you look carefully, you can see it already. In fact, see if you can pause for a minute. See if you can see how this picture causes this to be falsified. For any epsilon, choose a small epsilon interval. If x minus a is getting very small, so here's a very small interval here. If I choose an x inside of this interval, there's my x. I've chosen x. Distance between x and a is less than delta. X is inside the interval. Do we have this happening? Does this cause this? Look. X is inside of here, but where's the function value? The function value is way honking up here. It's not even close to being the interval. You say, well, why don't you just pick a bigger epsilon? The thing is this. In order for this, that's what this any means. This must be true for any conceivable choice of epsilon. Remember, no matter what the magnification scale. In particular, it has to happen on all the very, very small magnification. Not only does it fail here, if I choose an even smaller epsilon, if anything, it's going to fail even worse. But look up here. Here, everything works perfectly. No matter how small the epsilon we choose, there will be a delta down here somewhere. There will be a small enough interval. And no matter which one of these x's I pick, I can pick any one of these x's I like inside of here, all those function values will be inside that interval. What does it mean for x to be inside this interval? Remember, this is delta, this is delta. If I magnify this picture, let me magnify that picture just to be sure. Here's A. This distance is delta. This distance is delta. X is here. The distance between x and A is less than delta. That's the fancy schmancy way of saying x is inside this delta interval. And let me magnify this. Here's L. Here's the epsilon interval. This is distance is epsilon. This distance is epsilon. And f of x is in here. Distance between f of x and L, this piece, is less than epsilon. So this is the fancy schmancy way of saying f of x is inside the interval, just like x is inside this interval. So that is what is required to make sure that this is a nice, smooth curve. This is the notion of what it means to say a limit. As you get infinitely close to A, the function value gets infinitely close to L. That's sort of what's happening here. And so we'll talk about this in more detail in just a moment.